In this screencast, I'm going to calculate the bubble temperature for a binary mixture using Raoult's law. So we're given liquid composition and pressure, equations for how the saturation pressure changes with temperature, Antoine equations. We want the bubble temperature, and we also want the composition of the vapor phase. This is ideal liquid solution. I'm going to do the solution numerically, even though we perhaps could do this analytically. But the idea is when we look at more complicated systems, have non-ideal solutions, we use the same approach. And so we might as well just get used to doing it numerically. The equations we have, of course, we have these two equations for saturation pressure. And then we have the Raoult's law, which says the mole fraction of the liquid phase times the saturation pressure is the mole fraction of gas phase times the total pressure. This is the same as saying that if you gas, these are equal. And we likewise have the same type equation for component 2. So this is the third equation. The fourth equation, well, we should list our unknowns so we know how many equations we need to solve this problem. Well, one of the unknowns is the saturation pressure component 1. Another is the saturation pressure component 2, Y1, Y2, and of course, temperature. So we have 5 unknowns. We need 5 equations. The final equation is Y1 plus Y2 must add to 1. 5 equations, 5 unknowns, nonlinear equations. Because of these equations, we're going to use nonlinear equation solver in Polymath to determine the bubble temperature and the composition. We could certainly use other types of methods to solve these equations. Polymath is particularly simple to use, and it'll be demonstrated in other screencasts. So if I do that, what I'm going to show you is the Polymath output. So first, let me show you the output on the right side. Here are the mole fractions, the vapor phase, and here's the saturation temperature. That's what we wanted to solve for. This temperature is in degrees centigrade. So essentially 80 degrees centigrade is the bubble temperature for this problem. On the left part is the Polymath program. And the way Polymath works is I rearranged all of the equations so 0 is on one side of the equation. For example, I write this equation number 5 as 1 minus y1 minus y2 equals 0. And then in Polymath, I write this as a function of one of my variables. It doesn't matter which one. I happen to pick temperature. I could have picked y1, y2. All that matters is I identify to Polymath what are the variables I'm going to change, and then I make an initial guess. So I make an initial guess temperature. Certainly the closer we are to the exact value, the easier it is, more likely the iteration is going to work. And so I've written each of these equations by doing the same rearrangement and then picking arbitrarily one of the variables to put in parentheses saying the function on the left side. And what Polymath is doing is making each of these functions as close to 0 as possible. Here it shows the final values, 10 to the minus 12, 10 to the minus 15. So quite close to 0. I've entered the 5 equations. Then I've entered also the explicit equations, information I was given. This runs essentially instantaneously in Polymath. And so we've determined now our bubble temperature and the composition of our vapor phase. If we have a more complicated equation where the liquid's non-ideal, we'd have additional equations in the Polymath program, but the concept would be identical.